When we do a document AI, a typical pipeline is something like this. You get a document which may have images, which may have text, right? So let's go back to the picture that we had in mind. You have a picture of, this is pretty fat. You have a picture of a cow. Oh, no. And you have a text. The cow. Yeah. Over the moon. So what you have to do is first recognize, suppose I give you the task of just identifying the text. You have to know where the text is. So I can make this over and over again, bit of things here. All right, you have to first detect, you have to create what people call bounding boxes. So you have to know this is a image, it doesn't matter, but this is the text bounding box. The most important thing is whether or not you capture the image bounding box, you need to be able to detect the text regions. So the first task is detect the text regions. Typically, this is a task of segmentation, right? It's a sort of a object detection task. And segmentation is a topic we are going to cover in great detail, either next week, actually the week after that. Next week also we'll do document AI, but it's a full topic. For now, I'll park that. The meaning is literally what the word says. What are the objects in the picture? There's a cow and there's text. So text object detection is the first thing. Then you would go through the optical character recognition, or the actual recognizing the text. 1, 2, recognize the text. And 3, so to produce some character streams, characters, it will produce characters, and then understand the text. Understand from the characters found in the step 2. This is what you do. Are we together? Now, traditionally, what you do is you tend to use, this part largely happens to be, people use things like OCR. So the OCR is an old technique that has been around for a very long time, as I mentioned, since the 1960s. Very imperfect, but it was a proof of concept that it could be done. After that, it has been evolving and getting better and better. One of the great breakthroughs that came was the realization that you could use CNNs to do some of the steps. So, for example, to recognize, to do segmentation, and it was the RCNN algorithm. I won't go through that. It's a RCNN is a paper that I have put. What I will do is, in the interest of time, I will create a video on RCNN, because there are 3 versions of it. RCNN, fast RCNN, and not pretty much from the same authors, faster RCNN. These are progressive improvements. And you see, as more ideas came into deep learning, they kept absorbing it. And so these things, by the way, are very much in use today. These are the workhorses of the industry. quite a bit done. Are we together? Now, the value of this paper is that it breaks out of that traditional mold. It says that in document AI, we have just assumed that we need to do these steps in this sequence. Are we together? What if we didn't have to? What if we used, and by now, like, since you guys are coming to this from multimodal learning, right, you can almost look at it. So think about it this way. We did blip 2 and things like that, isn't it? If you use that kind of a optics or reference frame on this problem, you can say, you know what, if I got labeled data where I would get this image and I would get the caption. Caption would be the text present on it, namely the cow jumped over the moon. Text is given. Now I have an image caption pair, and the rest you know what it means. I can start training it now, right? In an architecture that would have somewhat similar to Blip and all of that, Blip 2, and then you could put what would you put? For the image, you would put a visual encoder, right? Then you would put a decoder there, a text decoder at the final, except that this architecture is actually simpler. It doesn't have the in-between Q former and any of that. What if we could create an architecture, and this is a simple thing. You take the image, and how would you take the image and create an image encoder? And theoretically, you can use a CNN encoder, or you could use a transformer-based encoder. We know that, of course, you want to use a transformer-based encoder. If you do a transformer-based encoder, you would take the image and break it up into patches, right? What are those 16 by 16 patches, right? The VIT, for example. So VIT evolved into a slightly modified and better version, which is more or less the very popular standard swing transformer. I talked about it. What swing transformer does is it actually takes 4 by 4 patches and then merges patches, adjacent patches, and so forth. So sliding window, SW stands for sliding window transformer. But think of it as VIT with enhancements, right? With quite a bit of enhancements. So then I could use it to produce a hidden state, isn't it? And now think of a sequence to sequence model. What is a language model? You have an encoder in a language model. You have an encoder. You have a latent representation. It produces a hidden state, isn't it? And then what do you have? A decoder. You have a decoder, isn't it? So the idea that they proposed was quite interesting. And when you look at all of these things, Blip, etc., may feel that, okay, it looks logical, but it wasn't actually. It was quite a leap. In the document AI, people weren't thinking like this. They asked this question that suppose to the encoder, we give it an image, and this encoder is actually a swing transformer. And for the decoder, what they use is, they actually, it's supposed to be a text decoder, decode it into text, right? Produce a text out of it. Actually, what they did is they put a pretty powerful transformer here. I believe they put BARD here. BARD is actually internally encoder plus decoder. But they used it as a text decoder overall. What they're basically saying is, let's give this visual encoding as input to a transformer architecture. Let it go through encoder decoder, but we will treat it as one giant text decoder. Are we together? So obviously text will come out. Now the whole question is, how in the world do we train it? Very simple. Decoder. Now, what is the loss function we use in the decoder? Decoder will produce the next token, YT, right, or YK, token K, isn't it? And you know what the real token should be. So you can do your negative log, I mean, sorry, let me just write it out. Isn't it? This is your loss function, right? And summed over all the Ks, right? And you know whether whatever yi it is, I mean, I'll just put the actual level one hot encoding, but I don't tend to write it. This paper uses that jargon, but I don't, because it's one hot encoded. Only the correct answer's probability you care about. Is the probability of the correct answer high or not? Correct word high or not? Does this make sense, guys? So I'll put the K here just to make it look correct. Losses. So this is your negative loss likelihood, right? You compare it. Now, one of the questions that comes up in transformers is, remember, the decoder not only takes the hidden, whenever you treat a decoder, you cannot just use the hidden state, because then how would you produce the next word? If you give the same hidden state, it will keep on producing or repeating the same output again and again and again. So how do you produce the token that is different from the previous token? You take the previous token and you give it as an input. Right? That's the way. Except that there is a technique called teacher forcing scheme. Right? Let me talk a little bit about it. Teacher forcing scheme, and I added that actually to your course portal. I added a glossary there, and I just at this moment made one entry, which is so the teacher thing, so that you remember it. But let me explain that. So the decoder is this. The hidden state, of course, you'll give coming from your image. But what you do is it produces a YK hat. But actually, you know the ground truth. You know that the word should have been the cow, right? So don't feed whatever word comes. Let's say that it came out with the word giraffe. It believes that giraffe should jump over the moon, right? You ignore that, but instead give the real answer as the trigger. Right? When you give the real answer as the trigger, instead of the last generated token, then this scheme is called teacher forcing scheme for the loss function, for the decoder loss. It's somewhat popular. What is the advantage of it that you can see? Advantage would be that, you know, if you make a mistake, that mistake doesn't perpetuate more mistakes, isn't it? That's the advantage of it. You're always aligning it back to the ground truth. But how's the learning happening? See, how is the learning happening? Because you know the cow jumped over the moon. Right? This is it. So what do? You take the decoder, you give the hidden state of the image. First, you feed in the word, you ask it, you just say start. Let's say that it produced some word, A. You ignore A. Then you, next time around, so this is first stage, this will lead to the same hidden state going in this time. But this time, instead of start, you say the. And you expect B to come out. Hope that B is cow. But if it is not, you find the probability of the cow. Here, what you're looking for is the probability of the, right? And here you're looking at the probability of cow. And you compute your loss functions on this. This is your y hat. Are we together? Right. So that's how you keep training. Your standard negative log likelihood, right? Log of the probabilities of the correct answer. But the trigger point that you use in the decoder is the ground truth and not the prediction, last token prediction. And when you do that, then comes the interesting thing. How would you train this transformer? It becomes a little bit easier after that. Yes.
So the previous token being input is totally different from the ground truth being input, right?
Yes. Yes.
I mean, it's It's changing the whole.
Yeah, game. It's changing the game.
Yeah.
See, guys, let me do it step by step. The ground truth, let me write that down. Ground truth is the cow jumped over the moon. Right? What you do is, let's go step by step. I'll put the steps between lines. First time.
Sorry, I have a question on the who is giving the ground truth?
You know the ground truth. Because remember, what did I say? You take images and you take captions. You take the ground truth. You create pairs of image and the text written on it. You create label data. Okay, guys, maybe that also needs to be clarified. Let's get this very clear. What do you have? Training data. Data is what? Image and the text it contains paired. Are we together? So now we know that we have a lot of these images and text pairs as a data set. Now we are clear? So for any one data set, I can produce the image to produce the hidden state using an image encoder. Right? So I have the hidden state of the image. Are we clear, guys? You have used VIT, Swin, what you like, right? Or CNN or whatever you like. You have produced the hidden state of the image. At that particular moment, you are going into this is the text decoder. And even we use the word text decoder, in reality, we are using a full-blown transformer, but treating it as a text decoder. They're using BARD. It's your choice, by the way. No, you can put anything. Conceptually, it doesn't make a difference. So think a text decoder. Now, what will a text decoder do? Suppose I give it a start trigger, beginning of sentence trigger. I just say go. So it will produce the first word, isn't it? It will produce the first token. The first token, what will it be? It will produce a softmax of probabilities. And so it will produce the probability. The only thing that you care for is probability of given input, given image, probability of, well, I see the conditional probability. Can I just forget about it? I will just write it as a probability of the, right? Even though it's conditional probability, it will just simplify it and write it like that. You will get to that. And it may so turn out that the correct answer was probability of if, let us say if was greater than probability of the, let's say by chance, let's say this is true. So therefore, what is the token? As from a practical perspective, what token has the decoder produced? If it has produced if. So now what happens is, so this is step one, number one. Now, when I go to step number two, I have a choice. I still have my image encoded. That image the encoder has produced. I'm fine, isn't it? I still give it to my text decoder. But I have a choice at this moment, isn't it? Here, I can give either if or the. If is the prediction, isn't it? It is the prediction token, predicted token. Let me just mark it, predicted token. The is the ground truth. So traditionally, normally, conventionally, you would give the predicted token as the input. Are we together? Right? You would give, in a normal sense, if you give, when if is used, let us say, when predicted token is used, right? And remember, predicted token is what is the only thing you will have during inference time. Now, then it is customary. This is what you do. It is the customary way to do things. Does that make sense? That is what you would do. In fact, at inference time, you don't have a choice, but we are in training. So in training, what can we do? We can do two things. We can instead, if we give the, actually, I shouldn't have picked the word if. It keeps coming up in my text. Yeah. So if we give the, we are supplying the, providing the ground truth token, isn't it? We are providing the ground truth token, which is non-customary. Which is a deviation from what you would have expected. Does that make sense, guys? And so let us say that we produce, we give it the, and so we go to step 3. So here something comes out. Let us say that, sorry, not here. Here something comes out. You have a probability of cow. The next word is supposed to be cow, right? And let us say by chance it produces giraffe, right? Let us say just by chance giraffe happens to be greater than peacock. Right? Let me put a sadu face here. Right? So suppose this were true. Then once again in step 3, we have a choice. Step number 3, again we have a choice. HI is going in, the same encoding of the image is going in, text decoder. And now the question is, what do we trigger it with? Right? What do we trigger it with? So we have a choice. We can give, if we give giraffe, if we give predicted token, same argument applies. Token giraffe, it is again the customary way but if, oh, what just happened? But if, but if we give the ground truth cow instead, we can choose to give it, right? It is again non-standard. So if we repeatedly, instead of giving the prior predicted token, we give the ground truth this method, then this method we are repeatedly following is called the teacher forcing scheme, right? It's a choice. Actually, if you go back and look at the original transformer, I think they use the teacher forcing scheme itself to train the original decoder. Yeah.
So
I'm not sure, but I'm pretty sure they did that.
in the subsequent call, okay, not only that the new word, but we give the previous as well. The second time the cow, we give like both the and cow.
No, you just give cow. You just give the cow. Right. So in other words, so anyway, that there's a possibility to give both, but in the simplest version, you just give the last token. So it's myopic versus non-myopic and so forth. There's more going on here.
So Asif, like, so mechanically, how do you input that? So like during the training process, you kind of override some things?
No, you know the ground truth. You have a data structure and you have a predicted. You just pick the ground truth always and feed it in the code. Instead of feeding the predicted, you always feed in the ground truth to the decoder.
Right, but they have to visually see, right?
No, visually it's a machine. It's running headlessly somewhere on a GPU.
Correct, that's what I'm trying to visualize how this correction would happen.
No, what? Imagine that you have a variable, an array containing the ground truth tokens, right? Every time you have to trigger the decoder, just plug the word from the head of the array and remove that token. Next time, whatever the machine produces, next time you want to trigger it, plug the next ground truth word token from the array and then feed that in. That's it. Yeah.
So what
And-
happens in the vector space if you look at it, like is it going to be like next token you go to a similar KNN kind of a thing, get the next one?
No. In this case, remember it's a decode. So you're not trying to embed it any vector space.
Just decoding.
Just decoding it. So guys, and of course you use the loss function remains the same. Loss function is always negative log of the real thing that it should have been, isn't it? For example, the first one would be probability of the, right, plus log probability of cow plus log probability of jumped plus log probability of log p of over. You get the idea, right? Is the summation of these terms. That's your net loss. And so if you know the loss, you can do gradient of the loss, backprop it, backprop this loss, and update, learn. It's easy. Easy? Yeah.
So, will we train the encoder as well as part of this?
Let's find out. Generally, you don't train the swing transformer. You just train the decoder. Right? But let's see. I'm pretty sure you don't touch the encoder. Usually encoders have been trained with a lot of effort, and usually you don't open out the encoder easily, but we'll find out. It's been a long time since I read this paper, and when it came out, let's carefully read through this and see what it is. So this is a big picture, I remember, but so why is this paper important, guys? See, people had just assumed that for visual document understanding, let me throw a term here, which is used quite a bit in this space. VDU. What does it stand for? It stands for visual. What could D be? Document understanding. Right? So get used to this term. It's used very often in document AI. Are we together? So when you talk about VDU, people just assume that it is a pipeline in which first you find the bounding boxes. You recognize where is the text, right? Text bounding box. And then you do OCR. I mean, you recognize what's written in that region, right? And then you take all those characters together and make head and tail out of it. Right? You understand it. Three-phase approach. It was a given. The reason and what was there is OCR was considered unavoidable. People said, of course you have to do OCR. And there were commercial OCR softwares and this. OCR has a lot of problem. If you have ever used OCRs, and especially if you have paid for it, you realize that it sort of works, right? It's never perfect. It sort of works. It is at the level that it's practical, it's useful, but it needs post-processing corrections. Also, OCR is language specific, right? More specifically, you change your fonts and your OCR performance will change, right? You use a very common font like Arial or something like that, it does well. You use a funky font and it goes for a toss, right? For what I call low resource languages, where data sets are not available for training it, it's pretty hard to train these OCRs. So this is very expensive to train. It takes massive amounts of data to do. And for some languages, it struggles. So for example, for Chinese and Korean, OCR has struggled quite a bit. Can you guess why?
Context.
It is similar point.
The characters are complex. Like, for example, in Chinese, they actually represent something. A dog is one character. Right? You don't say D-O-G. There it is. A house is one character. So they have a pretty complex character set. So OCRs don't do so well in that. So OCRs were considered necessary evils. Everybody needed them. And well, the performance was what it was. Are we together? And so the reason this paper is important is I'm essentially leapfrogging a whole generation of work that was done. This paper says, what if we look at the entire document AI as a multimodal learning problem? Are we together? What if we treat it as a multimodal learning problem, right? Think clip is there. From there, we are moving all of these blips, and a lot of this thinking was happening. A lot of these groundbreaking works happened at more or less the same time, right? So the moment you pose it like that as a problem in multimodal learning, given the fact that you're just coming from multimodal learning in the last few weeks, does it look very possible? And that is the groundbreaking thing. You know that something is groundbreaking when in its very simple implementation, bare bones, simple implementation, it already goes and achieves state-of-the-art performance on document AI tasks and benchmarks. Right? So subsequently, there has been enhancements and improvements and this and that. And so if you go to Hugging Face, you'll see a whole family of donut models. Right? I actually had planned to bring donuts for you guys, but I forgot. So, this is the big milestone, guys. Really, it's a big milestone. So the thing is, you're entering document AI. So obviously, you haven't yet been pickled with the idea that OCR is something that has to be done. Or how many of you have been doing OCRs in your company? You guys have been doing it, right? And I'm sure you believe OCR is necessary.
Yeah. Yeah.
Right. So that's a reason I'm bringing this. It's a seminal paper, and therefore, I know that you guys struggled doing that first assignment. Do you think it was worth it now in hindsight?
Yeah.
Right. Okay. Let's read. Should we read this paper carefully, or now you know all about it? Let's move to the next one.
So one basic question that I have. What is the base difference with OCR with this thing? So what does OCR do that this does not do?
OCR will just emit out the characters. That's all. It won't understand it in a more logical way. So you will see it as we go through the details. So OCR is a very primitive, low-level thing. Okay, here are the characters. What is it? If you say, what is the price of, what is the total amount I pay? It does not do understanding. See, it just does character recognition.
Yeah.
Text recognition, but not text understanding.
No context, okay.
No context, no understanding, basically.
So say you had a slide set. Slides have text, it has tables, it has diagrams. So would Donut actually take the whole thing and make sense out of it?
Yes, very much so. It's a piece in the puzzle, but a very important piece in the puzzle. And so it is just amazing, actually. Some of these papers, it's not just one. The papers that I have put for you in this field, document AI is a whole field. Like I said, right, I used to give a course on document AI. I've condensed it down for you guys to 2 days. Right? The papers that I've put there are all big milestones, but you'll see more fun as we go along. You'll see more interesting things come out. Yeah? But hold on to your breath. And now you realize why the title itself is a big surprise. It starts with the word OCR free, document. Right there, it's like, what? That's not possible. That would have been the traditional reaction. That's not possible. Understanding transformer, while it not only can do things without OCR, it can even understand it. That used to be a downstream task. So what people were doing is when transformers came out, if you look at the prior work, people were saying, okay, let's use transformers to create better OCRs, right? So what are the two main tasks in the OCR? Text detection, like this is the bounding box for text. This is the bounding box for text. And then text recognition. Locate it, recognize it. For both the things, you can use transformers. And so if you look at the prior papers to this, people were already beginning to use transformers to do better OCRs. And then comes this paper and say, why bother? Let's treat it as a multimodal learning problem. Right? You see a complete shift of perspective. Right? And the value of this paper is literally that. It's a shift of perspective. Because the moment you look at it through the lens of multimodal learning, and especially with the background that you guys have been filling up in the last few weeks, it begins to feel natural that yes, it can be done. So obviously, this thing is a big team research. Let's go over it carefully. The abstract is good. Understanding document images, for example, invoices. Invoices, I don't know. I almost suspect that many people think that document AI is nothing but invoice processing, because it seems to be or receipt processing. It seems to be the dominant use case. Right? Okay, but there is more to it. Understanding document images, invoice example, is a core but challenging task since it requires complex functions such as reading text and a holistic understanding of the document. Do we agree? For example, if I were to ask visual question answer, how much did you pay at the restaurant? On that invoice or in that receipt, let's use the word, there can be many line items and numbers scattered. How would you know which one it is? An OCR tool cannot do it, right? But you need some visual, language understanding tool to decipher and figure out what must be the total. Are we together? Right. So it needs a holistic understanding of the document or the text thereof. Current visual document understanding methods. Oh, did we encounter video before? We talked about it. Methods outsource the task of reading text to off-the-shelf optical character recognition engines and focus on understanding tasks with the OCR out. So it's a two-force thing. What you do is, if you want to do document understanding, visual document understanding, you'll first have the OCR text come out, and then you'll make head and tail out of the text.
But for that, we can use the CNN itself, right? So why you do the OCR?
You can, initial, all the prior OCRs were implemented as CNNs.
Oh, okay.
Remember, OCRs have been there for for a decade, for almost a
Began this, they
decade.
will be using the CNNs.
Yeah, it was using the CNNs. Right. Although such OCR-based approaches have shown promising performance, they suffer from high computational costs for using OCR, which is true. OCR is actually computationally slow and expensive. Those of you who have tried doing OCR know that just one page OCR takes a second or two or more. Right? Inflexibility of OCR models on languages or types of documents. We talked about that. And as some of you know, right, if you give it an image that is skewed, slanted, weird, the OCR performance begins to degrade. Just crumple it a little and it won't do so well. Inflexibility of OCR models on languages or types of document, OCR error propagation to subsequent process. So see, if the OCR read, not the cow jumped over the moon, but it said the giraffe drank water from a lake, whatever it is, something completely different, or it jumbled up the words. And suppose a downstream task is, what was the cow up to? You would be totally lost. There is no cow there, right? It's all about what OCR has given you is something all about giraffe. Hypothetically, I mean, cows and giraffes are hard to mix for an OCR, but let's say I'm just sort of giving you an illustration. In other words, any errors in the OCR, right? So let's make it more realistic, right? Eats, shoots, and leaves. Suppose after eats, the comma is there, it would be. So let's say that in one version, it is eats, shoots, and leaves. You're thinking of what? A panda. In the second version, if after eats there's a comma, that's a rather murderous panda if there's one, right? And so, point is, can an OCR miss a comma? Easily, isn't it? And so the downstream task of understanding would have a wildly different interpretation. So this is actually one of the subtleties of it. Language, sometimes small things matter, and small things can be missed by an OCR, completely altering the meaning of things. In invoices, for example, you say, suppose you have a classifier that says a petty expense, anything below $100, or needs review. And your question is, does this invoice need review? 1 0 that was faded out or not quite there, or I don't know, what OCR missing a 0 can make quite a difference. Right? So that's pretty much downstream thing there. To address these issues, so now they say that to address these issues, in this paper, we introduce a novel OCR-free video model named DONUT, which stands for Document Understanding Transformer. As the first step in OCR free video research, we propose a simple architecture with a pre-trained objective, i.e. cross-entropy loss. So typically with the decoder, anyway, you use, when you train a transformer, what do? What's your objective loss? It's a cross-entropy loss. So this statement hardly needed to be said. A donut is conceptually simple, yet effective. That's a crucial word, guys. When you see the architecture of donut, coming from multimodal learning, you'll find it to be dead obvious. Very, very, like all great breakthroughs, are very simple to understand and only in hindsight. Donut achieves state-of-the-art performances on various video tasks in terms of both speed and accuracy. And this part is important. Not only does it beat it in accuracy, but even in speed. Right? In addition, we offer a synthetic data generator that they call SynthDog. We'll talk about that. Yeah. But one of the nice things about it, which they sort of allude to, helps the model pre-train. It turns out that this architecture is far more easily adaptable to different languages and domains, right? Because by now you know all this multimodal fine-tuning, right? In fact, you literally did that exercise a little while ago to fine-tune the model. So let's look at it. The introduction, I won't go through the whole paper, but just the introductory part is important. I'll read through it. Document images such as commercial invoices, receipts, and business cards are easy to find in modern working environment. To extract useful information from such documents, video has not been only an essential task for industry, but also a challenging topic for researchers, with applications including document classification, information extraction, and visual question answering. So you go here and look at the typical scheme, guys. Do you see that you have a receipt? Do you see a receipt? And there's some background clutter, but the receipt is there. So what is the first thing you have to do? The traditional way of a traditional document processing is, first you notice that you find the masks, the regions where text is there, right? That's sort of a segmentation task, a mask finding task. Then you have to detect what text is there, right? And so each box is passed to a recognizer to comprehend the text. So it will come up with nothing but a list of text. You see, these are the words found. B box, bounding box, bounding box, bounding box, and what was the word in each bounding box. Then you have to, so that is pretty much somewhat like what OCR produces. Now comes the task of understanding it. You finally process it with the understanding thing that will produce it in the structure that you need. So the word, from that you have to infer that the name is this, the unit price is this, understanding part comes. Are you getting that from the receipt? That's when the understanding part comes. So it is a two-phase model. You have an OCR and a downstream model. You look at this, guys. This was the state of the art prior to this paper, right? Whereas what Donut proposes is just one model, end-to-end. E2E is the end-to-end model, a single model. And the benchmarks speak for themselves. Look at the memory utilization, much less. Time that it takes to run, number of seconds per image, again, much better. And accuracy, what is surprising is this part, that something in its very first implementation, just at the idea, like a concept, we can do this, and already it's beating the state of the art. That's when you know that it's a good idea, isn't it? So let's move forward. The current video methods solve the task in two-stage manner, reading the text in the document image, holistic understanding of the document. These are the two stages we talked about. They usually rely on deep learning-based optical character recognition, OCRs, for the text reading task and focus on modeling the understanding part. For example, as shown in figure 1, a conventional pipeline for extracting structure information from document consists of 3 separate parts: text detection, text recognition, and parsing. However, the OCR-dependent approach has critical problems. First of all, using OCR as a pre-processing method is expensive, computationally expensive. We can utilize pre-trained, off-the-shelf OCR engines. However, the computational cost for inference would be expensive for high-quality OCR results. Plus, most of the OCRs that tend to work really well immediately become commercial. Right?
Basil, the previous page, when there was a receipt, it was scanning. There was a quantity, some food, and then the price. How did it understand that? What was the unit of measure and to extract the unit price from that receipt? Yeah.
So, see, if let us zoom into this. You see that there's more information missing here. We would assume that somewhere in there, that unit is also mentioned, right? So that's that.
And then there was some logic which would have communicated to the program that this.
No, not logic. That's where a transformer comes in. Remember, transformers are language models, right? Language models can take basically think of this. So this part of it's a good question actually. This part of the journey, just think that if this is the input, I train the machine to take this as an input, a decoder, right? So you assume that this is the input training data. You force it to produce this as the output. So you can train it to understand this, right? So you can do that. LLMs do good at that. Okay, so we move forward. The computational cost of inference would be expensive for high quality OCRs. Moreover, the off-the-shelf OCR methods rarely have the flexibility, and this part I'll highlight. It's not just the cost, because you have hit a wall. Even if you were rich, off-the-shelf OCR methods rarely have flexibility dealing with different languages or domain changes. which may lead to poor generalization ability. Right? If we train an OCR model, it also requires extensive training costs and large-scale datasets. OCR is also hard to train. Another problem is OCR errors would propagate to the VDU systems and negatively influence subsequent process. Downstream transformer understanding part is affected by what the OCR produces. This problem becomes more severe in languages with complex character sets such as Korean or Chinese, where the quality of OCR is relatively low. I can tell. I tried at one time very hard to learn reasonable vocabulary in Chinese, and I would try and practice the pictographic, the character writing, and I would make so many mistakes. My Chinese friends would be, and not to mention that my intonation was completely wrong. So it's a very intonation-based language. I thought I was saying it right, and they would burst out in laughter. So, well, that's a separate topic. To deal with this, post-OCR correction module is usually adopted. However, it is not a practical solution for real. See, first OCR has a weakness. You bring in OCR, and then you try to fix it with a hack, right? Something to remediate. You bring in a remediation after that. Not a good idea, right? We go beyond the traditional framework by modeling a direct mapping from a raw input image to the desired output without OCR. We introduce a new OCR-free VDU model to address the problems induced by the OCR dependency. So they're basically saying OCR, let's get rid of it. I hope the message is clear. Our model is based on a transformer-only architecture referred to as document understanding transformer, following the huge success in vision and language. We present a minimal baseline, including a simple architecture and pre-trained methods. Despite its simplicity, our donut shows comparable or better overall performance than previously. So now the next two paragraphs are the only ones I'll read. After that, we'll move on. We take pre-trained and fine-tuned scheme on donut training. So there are two phases. They're going to do it in two stages. In the pre-trained phase, donut learns how to read the text by predicting the next word by conditioning jointly on the text and previous text context. What does that mean? Well, it's a little technical word. See, guys, all he's trying to say, they're trying to say, is that the donut learns to read the text by what? You give it an image. So image embedding was coming. And jointly, what else was coming to you?
Text.
The text was there, right? You're conditioning jointly on the image and the previous text, right? Context. Donut is pre-trained with document images and their text annotation because somebody has given the text, right? The answers, the labeled text. Text annotation is the text. Since our pre-trained objective is simple, reading the text, we can realize domain and language flexibility straightforwardly pre-training with synthetic data. So guys, what can you do? You can just cook up your own text for any domain, for any language, and then plant it on some image, isn't it? So you can easily generate tons and tons of synthetic data, even for a low resource language. So let us say that all of a sudden you decided that now you need to write like a framework, document AI for Nepali. You look around, how many of you have encountered any Nepali document data sets yet? None, right? So, well, here it is, just synthetically generated. All you have to do is take Nepali text, just take some random picture here and there, just plant an image on it. Plant the text on that image. And then now see, you have training data, isn't it? You have an image and text pair.
Asif, why is this sounds like fine-tuning.
No, you generate, this is the main part. We'll come to that. The fine-tuning here means something. We'll come to that. So,
That's a good question. Standard text extractors, the default they will use OCR if they support an image format.
yeah, most of them used to be OCR based. Actually, this is one of the things. I'm taking you literally to the cutting edge at this moment. Not many people have yet adopted it. Right? So what happens is that, see, the world is divided into, it's a bimodal distribution. There is a small crowd that's very active and on the state of the art, and they keep looking at the latest in Hugging Face and getting involved with research and what models have come out. They're usually a few years ahead of the rest of that, the other distribution of people, right? Who will, let us say, in a few years, wake up to the fact that, oh my God, there are some tools that don't use OCR. So that's how it goes. Yeah. I am told that in some domains, you can literally take a paper that is 2 years old, adapt it to that domain, just literally do domain application of that work, and nicely publish it in the journal of that domain.
But
They're so far behind.
in this case, like when they say OCR free, but still for bounding the text, they're using OCR.
No, they're not using OCR. There is no OCR. Think about it. Look at the architecture that I gave you.
OCR uses edge detection and all that.
Oh yeah, bounding box
Yeah,
and all of that. None of that is being done. So what happens? The architecture.
The green text.
Yeah, that is it. So OCR is made up of two texts. Where is the text? And what is the text? First, where is the text?
That is
Here's the box. That is part of OCR. OCR is made up of two parts.
Okay. Where is it and what it is?
What is it?
So they're not using what it is.
They are not using even where it is.
But where it is, the bounding you need to have.
No, you don't need to have. That's the magical thing. Remember, I just taught you multimodal learning. All it does is, it says, I don't care where the text is. I can just tell you, I will just generate, out of my hat, I'm going to pull out a string. Right? And I've been so trained that wherever it was in the image, the string that I'll pull out of my hat will be the string that's there in the image. And I wouldn't bother to figure out where in that image that string is. Do you notice? What am I trying to tell you guys? Look at this. This is the important thing, guys. What am I in this whole thing? Do you notice I'm telling you that image encoder, this is multimodal learning. In multimodal learning, you never went for the bounding box, right?
That's correct. So the hidden vector, what we are getting, right? So
It's just
as
a
an
hidden,
input,
it's just a
that is-
encoding.
Yeah, encoding of an image.
Yeah. Right?
Okay.
Within that encoding is,
So that is could be like a VIT or
it's a VIT. It's literally a VIT enhancement called Swin transformer.
okay.
So their results show that Swin does best. The Swin, by the way, anytime I use the word VIT in practice, go use Swin. Right? Because Swin is better.
Just tell me one thing. I'm just getting confused with this mapping thing, text to image.
Mhm.
So in this case, there need not be a relationship between the text and the image. That is, the text are putting in that the explanation that the image and text that text need not have any relation to this image at all. Only that by convention is being related.
Yeah. So Gopal asked a very interesting question. He says, while training it, wisdom is in actually the labeler, the guy who's creating the data, actually honestly putting the text he's seeing in the image. But what happens if you create a data set in which the text has no bearing to the image? Well, if it has no bearing, the machine won't learn anything, but you could do something very funny, actually. What you could do, and I think it's an experiment we're doing, suppose all the images are written in English, all the text in the images are written in English, but you insist on giving it all the text in, let's say, Tamil, right? And then train it and see what happens. Actually, why don't you do that? Donut fine tuning.
Probably a translator there, right?
Yeah, you basically will end up cooking on not just understanding an image in Tamil,
maybe like inventing a new language.
right? Or any language. So ultimately, see, training data is king, because what is it doing? It is coming up with a very abstract representation, decoding it into another language, into whatever language you give the training data in.
Yeah, that's what I was trying to get to. There is actually the vector that's coming out
Yeah.
from that encoder. You just try to map it with some kind of decoding, which there is no tight bonding between.
There's no tight bonding interest. And this is one of the things about transformers that's so mysterious, that they're so, at some time, right, you know the whole of it. You know exactly how it works. And then you realize that, wow, I still could do this.
So on this paper,
Yeah.
on the left side, so the figure 1 is a conventional method
Yeah,
which uses the OCR.
OCR.
So this
So
is where I got
basically-
confusion. So, but
Yeah. So you're basically saying this goes away.
okay, got it.
This goes away, right?
Yeah.
This is what we are going away with. And so, what is the core contribution of this paper? The contributions are summarized. So, this is the way you notice that all the papers in our field are written like that. In the introduction, you summarize the key contributions. So, it's making four contributions. First of all, it proposes a novel OCR-free approach. That's the core of it. I wish they had used the word. I think they have used the word, but it's basically a multimodal learning approach. If you are familiar with Blip, etc., it's very resonant of that. To the best of our knowledge, this is it says, to the best of our knowledge, this is the first method based on an OCR-free transformer trained in end-to-end manner. Second contribution is, and that is true, it really was. I mean, now it is considered a landmark. We introduce a simple pre-trained scheme that enables the utilization of synthetic data by using our generator, SynthDog. Nice name, right? Nice buzzword. Okay. We show Donut can easily be extended to multilingual settings, which is not applicable for the conventional approaches that need to retrain an off-the-shelf OCR engine. Again, a big thing, right? First of all, data generation is easy and training Donut is easy. In a traditional setting, you can't because OCRs have to be trained language by language. So it speaks to the flexibility of this model. Third contribution, we conduct extensive experiments and analyze on both public benchmarks and private industry datasets. We show that the proposed method achieves not only state-of-the-art performance on benchmarks, but also has many practical advantages. Example, cost-effective in real-world applications. Guys, did you realize that all of you managed to run it on your commodity hardware, right? Yeah, go ahead.
I have a question about the previous thing. So I was wondering what the relationship between the basic token and the boundary is.
You try to make them closer. That's where the loss function is. So you basically say, hey, I was expecting cow. You are saying the probability of giraffe is 0.7 and probability of cow is 0.3, right? You made a mistake. And how much of a mistake you made? There's a mathematical expression for it. It is the negative log of 0.3, what it should be. Probability of a cow happens to be 0.3. Let's say in this scenario, so you would say negative log of 0.3. Because if it had said that the probability of cow is 1, log of 1 is 0, isn't it? So negative of that also would be 0, right? And so you would say there is no loss, there's no mistake. But because you said 0.3, right? 3 over 10, well, that's bad. That's pretty bad, right? Because that's log 10 minus log 3. Yeah, that's the idea. And you learn from that. Okay. All right, guys. So now, what is the method? This is the architecture I was telling you about. You have a transformer encoder. Think this is your visual encoder, right? That is it. You give it the output of it, you give it to a decoder. Now, based on the task, see, do you notice that, guys, you can train it for 3 different tasks: classification, visual question answer, and parsing, by literally prompting it like this, right? If you give it the classification, you force it to produce, it's a receipt, right? So it is doing, do you realize how sort of versatile it can be? It will produce this output. Because what does a decoder of a transformer do? It is just a token sequence generator. You train it to produce this. If you give it a question, and remember, this is the answer, you just say, okay, answer now, practically. Then it answers this, second one. And if you say parse it, then it should create a nice JSON data structure, or it should produce something that you can then convert subsequently to this, and this, which is easy. Yeah.
There is something called annotations.
Annotation is basically the answer, the text that somebody has entered. So in their thing, what they're calling is given image, and whatever was written on the image as annotation. I'm calling it text, they call it annotation. Because in the language of labeling world, right? You say, I'm sending the images for annotation.
Right.
And labelers sit and annotate.
Is that a mandatory thing and for the machine to understand?
No, unless you give it training data, you give it the answer, how will you train the machine?
Exactly, so it is a mandatory.
It's a mandatory thing. Yeah. You need that label data. So here's the thing. In this field, right, people always find clever ways. First of all, how would you, for example, you want to train it on Nepali. You can look around, you won't find those enough data. It's a resource poor language. So what can you do? You can turn the tables. Just go generate a lot of Nepali text, which should be easy because there's text available. And then just take lots of images and go planting these text on those images. Right. And now you have an image and a text pair. The image will be image and the text you'll call annotation.
Now, could we do that through another translator? So like if you take a receipt in English and then do an English to Nepalese translation and it could still work?
It could work, but in the image, it's still written in English, right? That's it.
So that become a pipeline, right? So after decoding to the English text, you can feed it into the
Translation.
pipeline.
Yeah. So you notice that your output sequence is this, and you can then translate it to whatever you want to translate it to, right? So you see, guys, how beautiful this thing is. And what they do here is I'll fix it. I'll remember this paper, and I'll be happy to correct myself. But if I remember, they use BART. BART. BART is both an encoder. It's a full transformer, basically. Don't confuse it with BERT. BERT is only the encoder. Yeah. So, and guys, if you want to play around with it, you can cook up your own and try to play with it.
So in the blip, it produces like only one task downstream. Here they are getting three.
No. It was also multi-ability. But we used it. Remember, we did visual question answering. We did captioning. We used it for many.
Yeah, question answer.
Yeah. It was, in fact, I would say that it's a little bit more involved than this. Right? So guys, this is it. Now, of course, the state of the art has moved forward. Right? Now, for example, you would like pretty much feed it into a visual, like we now are talking about visual LLMs. This whole thing, this idea has been taken forward. But you can see how it all is starting out, isn't it? So encoder, guys, is this statement self-evident by now after reading clip and knowing all of those things? Is this self-evident? What are we talking about here? This is right. What is this whole business of this funny R and so forth? Okay, 1 second. What is H cross W cross C?
So the H is, I think, like a hidden vector.
No.
No. Okay.
So guys, you have an image. You have an image. Oh, sorry. You have an image of a cat. Right? It comes in RGB channel. So there'll be three. It is actually three images, isn't it? These are the channels. See, every image has a height and a width. That's what it is. So you agree that every input vector belongs to a space, which is this, right? And it produces an embedding vector, which is a single dimensional vector, d-dimensional vector z. I use the word H, they use the word Z. But so H and Z are both very common in machine learning literature for the latent states. Where N is a feature map, blah, blah, blah. You could have used CNN or transformer. Yeah. And they say that they use the Swin transformer. Swin is basically, think of it as the better width. It uses a sliding window argument and hierarchical argument of that. So everything keeps evolving. Swin transformers, blah, 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 blah. And then it explains what a swing transformer and how these things work, which I trust you guys don't need to be explained. You know VIT and all this quite well now. What is the decoder like? Given this, the decoder, oh yeah, it does use BART. Yeah, as one of you pointed out, it does. We use BART. So they remember BART. You may, in case you're getting confused, hey, you can say, hey, BART is a full model. It has an encoder decoder. No, that's all right, but you can still treat it as far as you're concerned. Put a blanket all over it and say this is a decoder, right? So then the rest of it is easy. Output conversion, start minor technical details, pre-training. You use some data, you generate some data, you also do it fine tuning. After the model learns how to read in the application stage, we teach the model how to understand the document image. As shown in figure 3, we interpret all downstream tasks as a JSON prediction task, right? So it came out with all your sort of a XML tag kind of a thing. And then from that, you can extract whatever data that you want, which is very common in the same thing. So here we go, downstream task and data sets. Let's look at some of the downstream tasks. A, what does A classify? Is it a form or is it handwritten? That's a document classification task, right? Leftmost, look here. So this is a classification task. Do we agree? If all you have to tell is whether it is a form or it is handwritten, then you can tell. It is a simple task. B, document information extraction. Very common, right? From your receipts, from your boarding pass, your driver license or passport, you extract info. That's that. And the last is visual question answer. You are given. So this is the most common task that you guys are thinking, right? And then the third is, which for many people comes as a surprise, that actually these transformers have become so powerful. You can just give it an image and ask it a question. What is the extension number as per the voucher? And here's the voucher. And it is able to answer it. Isn't that impressive? Pretty good, right? So these machines do visual. Let's see what's the accuracy in a moment. So this is it. These are the tasks. I'll jump straight ahead to the experimental results. Right?
Asif, one quick observation from an input perspective. These files are various sized files, meaning
Right.
with various dimensions. There is no standardization or whatnot. So that's really fascinating. It's one observation.
Yes.
Yeah, I
That's
did
right.
check some of those images, and they're various sizes.
Nice. Yes.
Suppose your all your images are feeding just English language, then do we need to train, or you can just because the text is already
No. See, remember they give you the synth dot. It's so easy to create data and fine tune or retrain this model. So first thing is that why give only English? If you want, just train it with a few more languages. Or if you want to make it language specific, if the data generation is easy, just go train it.
And all I meant was if you're introducing a new language, that's probably when you need to fine tune.
Yeah.
The existing language is nothing to do.
That's right. Yeah.
So Asif, I have a question. And when you are scanning those documents, some of those documents have the PII on it. So do you just to exclude that, do you just not annotate it, or what's a way to kind of not have that PII?
Just throw out those dots. What you do is what it looks like a passport or something. Sometimes, right, these are expired passports or expired documents that people have volunteered to give, or the government has decided it's public property now. Or more realistically, right, a lot of these data these are what you would today call deepfakes. It's very easy to produce those. In fact, the project that I'm going to give you, a clip data set, it will be a data set of 68,000 passports, images. and your job is to apply it and extract information from it. And let's see how well you can do it.
So in that particular example is you are reading the personal information, right?
Yeah, you are reading. You're reading.
But in the case of like you showed maybe that boarding pass there, where maybe the intent is not to read the name of the person or the passenger, but everything else.
Then you have to black out, because you don't want to confuse the machine to say that here is a text but don't see it. You have to black out.
Yeah, so you have to black it out.
Yeah. So when people see, there's a whole industry of people who sit and carefully produce label data. Right? It's their job that if they find PII, they'll block it out.
So the things, can this model say like, hey, which part of the image is the name found, like the top 10 pixels or something like that?
It doesn't give you the pixel, but it will point out, it will put a box around, or it can, these things are too easy, just to tell where the name is in a form, right?
So we can use this model as some kind of additional code to mask out documents.
Oh, yes. Those things are, and see, this is one approach, right? Remember, I'm reading only one paper because at this moment you guys took a lot of time with the homeworks, and it will take more time because it's your first day. I was over ambitious. Let's go over it slowly at the pace we can, because it's important to understand it right. But in the subsequent papers that I'm coming to, there's more fun stuff. Now wait for those fun stuff to come. Right. So today I'll just read 2 papers, guys, or maybe it's 4 o'clock already. I don't know. I want you to at least do the homework. So maybe only 1 paper for today. But let's look at the results, guys. Look at now let's see. Oh, look at this. The simple donut. Right? It's almost a donut without any sprinklings. Right? So already achieves. First of all, look at it. It's a small model, relatively. Right? 143 million parameters. The time in milliseconds that it takes to process is sub-second, right? 752 milliseconds, whereas all the other models, state-of-the-art models at that time were taking more than a second per dot. Second is 1,000, right? Milliseconds. What is the accuracy? Do you observe, guys, that it achieves straight off bat, achieves state-of-the-art accuracy in document classification? Isn't that impressive? It takes years to perfect.
But which was not created for this specific purpose is actually doing better than OCR. Like in previous, you have
no. What they did is you create a OCR pipeline using BERT, because BERT is a classifier, right? Also, so once the regions are detected, traditional OCR.
The traditional OCR is about 82% or something accuracy.
That is right.
At the previous
right. So what happened is that there was the traditional OCR, then people started using transformers to do better OCR, and then this paper came and says, why just forget OCR altogether? Right. That's a contribution.
So is this more of like a wrapper, or it's not a model in itself, right? It is more.
No, it is a classic multimodal architecture, right? In the style of Blip, for example. Yeah. It's a classic multimodal architecture.
Got it. It's an application of leveraging BART and eliminating the OCR concept typically.
Yeah. That's using a visual encoder and a BART decoder.
Got it. Thank you.
That's one question. So we're doing this semantic search. We are actually using Apache Tika and then extract to text. But let's say the text has labels. Let's say it's PDF with tables, tabular data, and all that stuff. Perhaps Donut will do better than just using Tika.
Yeah. So because the question
it actually adds the tables and can infer data from it. Right?
Yeah. So the answer to that is yes. AI systems generally do better than brute force systems. That's a given. The second part is that, which is more relevant, is that see, when the PDF is generated using modern PDF generators, it contains the text, so you can extract the text easily. That's why PDF reader can return you the text. But actually, the moment it starts having mathematical functions, etc., it doesn't do well. The next paper I was going to read, which was the Naugat paper, teaches a machine to understand mathematical notation and produce the source code. How many of you know the language called LaTeX or text? Can you imagine that it can look at a scientific document and produce text source code? LaTeX says source code. That is the next paper. So if you guys are willing to stay here till 7 p.m., are you all ready? How many hands up? Oh, okay. Lots of hands up. I would love to do the Naugat paper also, but before that, you have to finish all the assignments. You have to do all three. So we'll do that. It's great. But guys, I hope you are excited, suitably excited. I am showing you things that are genuinely very exciting in this field, right? They change the field. You see, it's a watershed moment. Forget about the old way. Here's the new way, right? So table 2, performance and base information extraction task. What exactly is there? Like this, think of it as your receipts, invoices, what business card, whatever, right? See how Donut is doing, right? Do you notice that once again, the timing is pretty good? Look at the performance. It's achieving state-of-the-art performance most of the time, in fact, all the time, right? In almost, in fact, all of these numbers, it's achieving state-of-the-art. It's beating everything, right? In fact, beating 2 of the algorithms that just came a little while ago, Spade and Wyvern. It beats both of them. Right? And document visual question answering. It's like, so look at this thing, this document. You see this document, guys? I don't know if you can see. Let me zoom in. You see, in this document, in such squiggly letters is written this thing, is zoomed out version. Dr. something J, Darby or something. And you ask it a question. You ask Donut a question. What is the name of the passenger? And it comes up with Dr. William J. Darby. You should surely reward it with a nice donut. Right? And that's the ground truth. Right? And the layout, by the way, we'll do the layout paper also. That misses it slightly. It just got Dr. William J. Jarry. Go ahead.
All this stuff will having almost a practical humanoid is not very far away.
It is not. I'm telling you. Did I ever tell you that your programming jobs are gone?
Yeah, multiple times. Thank you for saying again.
Yes. So guys, you realize that these machines have become insanely smart. A lot of the traditional things that we are doing sitting in companies, right? Forget about it. Here we go. Now, look at this. You see this tiny little thing written here? I can't make out what's written there, right? In that image is written Public Health Services publication number 540, revision this. And you ask very specifically, what is the publication number? Isn't it astounding that it comes out with the answer? Oh, wrong answer. That's all right. It came up with the wrong answer. It extracted, what did it do? It extracted another number in the image somewhere, right? But at least it knew that it is a number, right? Actually, for a first, like a paper that just come out, that just has a proof of concept is not bad, right? It is wrong, but it is pretty close to hitting it. And obviously, there has been refinement of this. I invite you to go check out the refinements on this model, right? And so in this particular case, the layout LM, by the way, layout LM is what? Layout LM is very, very good at discovering the layout of a document. Like, for example, when you say table, when your data contains, your document contains lots of tables and figures and something, what you need to do is And that is where actually, and this actually this example is very illustrative. What you want to do is you want to take a two-stage approach. What are the two stages you want to do? You want to use a layout engine, layout transformer, to extract the elements, figures, text, table. And then if it is a table, then use a table transformer. Table transformer is trained specifically to understand tables. Are we together? And layout transformer, the layout LM, language model, is specifically trained to understand the layout of the page, of the document. You see how it is, right? Everything is very good at its task. And in this particular case, a donut misses it a little bit. By the way, LM, I think, is in V3 now. Layout LM is in V3 now. So check it out. So further studies, blah, blah, blah. I'll let you read the rest of the paper. Then there's some more examples. Look at this. You see the examples of things that it is able to make head and tail out of? And but no, actually, this is an example of another tool that they created in this paper, SynthDog. English, Chinese, Japanese samples are shown. Although the idea is simple, these synthetic samples play an important role in the pre-training of donuts. So what you do, if you can, see, what are they doing really? They're just producing text and slapping it on something, isn't it? Like this thing on a garbage can doesn't quite make sense, but it does produce that. Right.
That's a good question.
Yeah.
So when compared to other LLM based models, like, I take a HTML or PDF which has the tables and stuff like that, then we feed into LLM and get the answers. That needs a little bit more work if they have tables and stuff like that. But here it seems like you don't need to do. There is no extra work. Is that correct?
Yeah, I mean, see, here's the thing. There's the good news and the bad news. First of all, it moves the state of the art. Nothing is perfect. If you want to really get it to perfection, and this is why, remember, I started this class by saying general purpose cloud services will never be able to beat you. Because why? If you're sitting there, you're very aware of the structure of documents in your domain. So you see a lot of tables and things like that. What will you do? You'll pre-process it with the layout transformer, layout model, right? Isn't it? It's common sense. And so by pipelining really powerful things that do one thing well, and then in the mix is donut, right? You will get really good performance overall. So, it's a very Unix-like philosophy. In Unix, what do? You have little commands, sed, awk, grep, but you pipe them together and you get your work done. And now I look at this some of these transformers, right? Quite literally as like those little Unix commands that make Unix so amazingly powerful. You just create a pipeline of those. And look at this, guys. Isn't it nice? Predicted ground truth. It got it right. Some things it gets wrong. So for example, here. Right? And you see this. So clearly it got it, as is obvious to everyone. It is wrong. No, it's, yeah. So I actually don't know this language well enough to tell that it's right or wrong. Yeah. Okay, of course, it's totally wrong. I mean, according to them, it's wrong. It's wrong. You can see that it should be this, and it is this. The second character is off. Destination, this and this. Actually, is this Korean or is this Chinese? Can somebody tell me?
Japanese.
It's Japanese. This is Japanese. And this one? This is
All three are Japanese.
all three are Japanese, really? Oh, because of the yen symbol, you could tell.
Yeah, because of the train tickets.
Train tickets, okay.
But Japanese people, they also use Chinese.
They also use the
Combine
Chinese
it also.
combined. Okay. Yeah, I'm told that Korean is much simpler.
But the last one, it says Beijing on the ticket.
Beijing, yeah, here, Beijing.
Shenzhen.
Oh, Shenzhen,
This is like a Chinese
Guangzhou.
one.
Yeah, it is Chinese.
So then is that money,
Chinese?
none of it, is that Chinese?
That is wrong, actually.
Oh no, maybe Y is for yuan, right? Chinese yuan.
You want, yeah, probably, yeah, you want, you are right.
Okay, that's right.
Not yet.
Yeah. So I have a close friend, a Korean friend, my graduate school, sort of a mate in my office mate, and who literally saved me quite a few times. Sometimes I would entirely forget. I would have a TA session to hold, and I would nicely be biking outside. And then he really saved me quite a few times. He would walk into the classroom and tell that today Asif has asked me to teach, and then just go ahead and teach it. So he told me something interesting about Korean. He said that he came from the royal family in Korea. Right? So he told me an interesting thing. He says a Korean sat down and created a simplified language, the Korean king, emperor of Korea. He had all the scholars come and said this language is too complicated. Let's create a simple language. And when he had created it, it speaks of the times and the prejudices of the time. He said it's a language so simple that a man can learn it in one day and a woman can learn it in 2 days. I wonder how the Empress took that statement. So anyway, there we go. This is it. Input image. So you notice that for English, it seems to be doing pretty good, except that look at this. Here, some information is missing, right? And the ground truth, the prediction is, the predicted value is 56, and apparently it should be 50. But can you guys tell that it was 50, not 56?
Even
So
humans cannot.
Yeah.
It's so obvious.
And here item is 1, and here the quantity is 1, and it says, what does it say about the quantity? Oh, it entirely missed the quantity. Yeah, in the date. So yeah, I mean, again, it's not perfect, but remember, guys, that when you look at the accuracy, right, of the extraction process, what was the accuracy or what was the extraction efficiency here? Or numbers, performance?
7 or something.
92. What it matters finally is better than the current one. Accurate or not.
Yeah.
As of October 2020.
Yeah, and things have been evolving since then. And fine tuning, okay, this is for table for normalized levels of similarity.
By the time there will be another state apart.
Yeah. So yeah, you can see receipt, the F1 and the accuracy is 88%, right? And on CORD it is 90%. And on some tickets, presumably because tickets are simpler to understand, it's 98% accuracy. But you know, there's still scope for improvement. So you guys still have time to create a better model and publish. All right, guys, I hope you had fun. I hope it gave you some insight into the world of document AI. So what I will do today is I will, jokes apart, it is 4:15. Please do the 2 assignments. On the Nougat, just go to Hugging Face Nougat page. There is a sample code. Run the sample code on a document. If not, I think the sample code runs it on the Nougat research paper itself. Yeah, right? But it's not predictive because Nougat research paper is fairly recent, and you don't get any value by producing LaTeX out of it or text out of it. Or pick a PDF of something ancient or something old, 100 years old or 50 years old, of which you don't have the source code available, and then it is more fun. Try it out and see what happens.
The Nougat paper works on images or PDFs?
PDF.
No, it does.
No,
images. You have to do PDF and make it into an image.
Yeah.
Image, yeah.
Yeah, it takes only the image.
Oh, it takes only the
Yeah.
okay, yeah. So try it out, guys. Please try it out and see what happens.
The examples are given the model. It says like image. Because I tried with another paper, which is a PDF.
Yeah.
It throws
No,
me an
no.
error.
But see, guys, how do you convert a PDF to image? Just PDF to JPG command, right? It will produce a directory of images.
No, I can create, but what I'm saying is again, it's not taking PDF.
It's not there.
Yeah, but if you do it that way, then that only looks for one page. But if you want to separate each page into an image, you have to get one image. Right?
Oh, PDF to image will create a whole list of images, one per page. That's it.
Wait, which way do you want? Do you want a list of images or do you want image?
No. You want to have a list of it.
Oh, just
You have image, the other text. What is that?
All right, guys. So with that, I'll end for today. See, guys, I have a request for you guys.
So can
One second. I have a request for you guys. Please do this. Can I assume that you guys will finish the 3 assignments? Please do that as a team, all of you. And then I'll release the project. The project has a huge data set of passports and driver IDs or something like that, passports, right? That of many countries. It's an interesting project. I want you guys to take it seriously, please. Huh? Now, the rule of the game is you're free to use whatever model you use, anything, use whatever you want, fine tune it, do whatever, and see how much you can extract from those images. Are we together? That's your project. And the winning team gets a really, really good support vectors marks. How's that? Right? So let's make it a competition. Let's make it a hackathon, the first hackathon. And we will have our Lal Kunal as the judge. He's going to judge that. He's an expert in document AI. No, really, I mean it. He has a startup on document AI.
Can I ask a question? Can we survey the room for the first exercise in those 3?
Yeah.
How long it took for people to train their model?
Yeah, guys, how long did it take you guys to train the model?
Yeah. After it takes 1 hour.
No, it took me 23 minutes.
After
23,
Yeah.
M2, M1.
I turned on MPS metal.
Even if you thought it, I think I see Apple takes that is the default.
So whatever the data set that we downloaded from the data, it took 23.
Yeah, it took you 10 minutes on a 4090. How did you know you were using 4090?
Because I tunneled into my home.
Oh, in your home 4090. That's good.
The other thing was initially directly the code, it was giving accuracy of 33% when using the Mac stuff and all. But after doing some small changes, now we are able. Then it was 66, and now finally able to get 75%.
Oh, okay, guys. What is the final accuracy?
This is output.
75. You guys also got 75. Oh, same team. What did other teams get?
Yeah.
What did other teams get? Guys?
So I wanted to know
Yeah.
whether
Right.
this is good enough or.
No, it's not good. Train mode. No.
I mean, on a Mac, right? I'm not trying to
See, here's the
get the
thing.
NVIDIA GPU.
In AI, the answer depends on who you talk to. If you talk to an engineer, he says, wow. If you talk to a product manager, what? So bad. Go do better. So guys, anybody else has the accuracy on the first assignment?
This is the right,
75. Okay, everybody got 75. Okay, good. So guys, there were some tips. Many of you hit roadblocks and you fixed those roadblocks. Can you please share it on Slack with each other, please?
No, this is
For Mac, I will share.
Yeah. And guys, please, I will post those onto the course portal so that they are permanent assets. And the other thing is, guys, do the remaining 2 assignments and be ready for the project. Now, one more final thing, guys. Please listen to me and let's have one conversation, guys. Guys, please listen to me for 1 minute. Guys, yeah. There are lots of papers, important papers in this field. I cannot cover all of them at the pace we are doing. I'm going to cover a few of them, but can I make a few of these as paper readings? Or if I have done paper readings of them in the past, I just leave it for you to read on your own. Or in the past, I have done paper readings for some of them. So can I just post the videos of those from last fall or something like that? I'll post the videos of that because that will save us time. Because if you look at it, we have, 12 important papers to study. Obviously, we won't get time to do all 12. I would like to do Naugat for sure. And one more maybe, but that's that. Huh? So try to read some of the papers on your own and watch the YouTube. I mean, the videos I'll post for those previous videos. All right, guys, that's all I have for today. Now, one final thing. There are these OCR tools. Do you notice that the moment you talk document AI, the most popular thing are the OCRs. These are the most popular open source OCRs. Tesseract is slow. Paddle OCR is good, pretty fast. OCR is PyTorch based, right? Easy OCR is also okay. There are trade-offs between them, right? This was the old way of doing it. What I'm going to do, I've started a book here in this, which is currently empty. But what I was thinking is, because there are so many papers, I would add a chapter with a video and explanation for each of these papers. Would that make sense? Like I will record the videos offline. Now I don't know when I'll do that. Most likely in May, because I may not get time to do those things right now. But I'll make this into a proper asset for you guys. Remember, guys, you guys will have access to this portal in perpetuity. Right? So it means that you can keep coming back to it and refreshing your knowledge. Yeah. So that's that. All right, guys. With that, any questions? Those of you who are remote, any questions before I end today's session?
This you directly, right? Data is there, and then we saw that. Yeah.
Any questions, guys, before I finish? Come again? Oh yeah. Oh, do you want to? Yeah, guys. Wait a minute. There is a presentation actually. Hamad has created some really nice open source project, and I would like him to present. He, as you know, is both a student and helping you guys as a TA and an intern here. So he's going to present his work right now. So I'll get off the audio and we'll now hear it from. Oh, you want to come here? Okay. Okay. So Hamad is going to be here, and he'll be presenting his work.
Image
Oh. This is all the space here. That's can someone submit the Zoom link?
That's the first thing, right?
You change locations. Okay.
What version of Python is? So go to what's the same? Okay. Yes, yes. Based on this. And then this way is needed later, not at this point. Yes. And then you may have done this. Yes. Is it actually?
Oh, yeah.
Yeah, we also actually you just talk it. Oh, it's okay. I mean, like, you type the whole thing. Okay, then just to make sure not mistake, go to the next one. Next one where it fails, remove that and then copy that. This option. Yeah. No, here you type it. Just clean it out.
Oh, wait, I found it, Roman.
I sent it to you.
Okay.
Doesn't copy.
Yeah. It's about second foot to the.
I just realized
Like
it's in the
just to-
course
so that
portal.
you
It's the
learn,
very
right?
first link in the course portal. Oh, no, it's, oh,
That's like, that's, I don't like this.
yeah, it's a
Sometimes
news.
it's like- Yeah.
So
That's all. I need to, yeah. I mean, nothing comes to me.
Folder. Can you see what's?
Yeah.
So it creates a folder called image folder.
No. Image folder is a feature on it.
Okay, can you guys see my screen?
No.
Yes, we can see your screen.
But we can't see on the.
Yeah.
Oh, okay.
You have to share your screen.
Oh, it's okay.
Is it vector splits?
So you have to share your screen. Yeah, I shared it. It's just not on the. Oh, there. Oh, that's easy.
But the channel just says T1.
Oh, yeah, right.
Oh,
nice.
nice.
Yeah.
We need to make him edit it.
Yeah, so stay close to the micro. Just turn the microphone close to you. That's
Okay, so this is more, I'd say, of like a concept of a framework than a solution to RAG.
Did you put your mic?
Yes, we can hear you.
Yeah, we can hear you.
Okay. So looking at RAG, like as a whole, you just need a whole bunch of libraries if you want to go end to end. So you would need your PDF parser, your text parser, and then if you want to pull images out, you need all of this, and then you need NLP libraries, sentence transformers. Then you need a database service. You need your vector search, and doing that, I say as like a simple developer's approach is not very fun to do. It's very long. So I've built this pipeline where all you do is import this RAG class, and it's connected to a whole bunch of API providers. So you can change this to say OpenAI or NVIDIA or Hugging Face, or there's a couple more.
Well, is there a way to increase the
Font size.
Oh,
Mac
yeah.
plus plus.
So you guys realize that he has implemented the whole project that I gave you guys?
Yeah.
And he has made a library out of it and made it so simple that you can do it in 3 lines of code now, Python code. And not only that, made it completely agnostic. It's pluggable with OpenAI, with local LLMs, with everything. I'll let him speak.
So the second command, the command to actually build the RAG database, you would run this .build command, and .build can take in a string. This string is this directory right here. This directory's got just a couple of, it's got PDFs, movie scripts, just a few documents. And so if you go and run this, this is running the entire text. It'll open the documents, clean the text, chunk, vectorize, and then everything goes into a database with a proper schema.
So he's taking our jobs now.
People have been bugging him too much, so he realized library.
So which database, what kind of database you used? MySQL, Postgres?
No, this is a library called Whoosh.
Which one?
It's
Oh,
a
Whoosh.
library called Whoosh. So none of this, the thing is, none of this is going to be production, like scale. This is so you can just plug in RAG and just use it how you want to in your code. So you see, this created a databases directory, which is the default. You can define wherever you want the database to go. So now we can test it by running results search, and then print the results. So it pulls up, and then if I run something like, so I put the CoStar paper, or not CoStar, the Quiet Star paper in there from last Thursday? Yeah,
Yes,
last Wednesday.
last Wednesday.
So if you go into search
The paper release, Wednesday.
Quiet Star, something like that, you'll get all of that as well. And you see it's all linked to the same document. It's pulling the proper chunks. The whole database pipeline is and then actually the search as well runs through a cross encoder that is re-ranked. So this is the ranked search that runs both your like Elasticsearch and the vector search. So now we throw it into the LLM that was initialized right here, which is just another one command.
Repeating the output.
No, so I'm just building a prompt. The only thing that goes to the LLM is a prompt. Okay, so this is, yeah. Oh, so this invoke command, it does the whole search. It'll put the chunks from the search results into a prompt that I've defined that makes it a little easier for the LLM to understand like what it's getting from those chunks, like comparative to your query.
It's called structured prompting, and you will learn about it in the LLM too.
So the next step is, that was the very like basic implementation. So if you want to take this now a little further, now I'm initializing 2 of these RAG pipelines instead of 1. One of them is connected to the NVIDIA API, and one's connected to just OpenAI. You can customize them because this is all prompting. So you write here, the first query is Steve. He's horribly unprofessional, not very bright, slurs most of his words. And then the second one is Asif. And it's the same database. It's pulling from the same vectors, everything. So you run invoke. Oh, oops. There you go. So
What does Steve say?
he says, so like Quiet Star. I think you're talking about that thing where you gotta train a model to like think before it speaks. So, and then you go and ask the same prompt to Asif. And it's a lot more complex. So he goes, is a technique for training language models to generate rationales or thoughts for each token in a text sequence, allowing the model to better understand and reason about the context before generating a response. And then he goes over the steps as well. And then you take that even further. And I've made something called Mixture of Experts, which is where I'm sitting at right now, what this mixture of experts does is you define your RAG pipeline as you did before. You can have 100 of them if you really want. You throw in, you initialize them. Oops. And then this one's using the Anthropic API, the second one. And then you initialize this mixture of experts. Throw these in as a list. Now, what this mixture of experts will do is it's its own LLM. It's going to take each response that those LLMs gave, their search results, throw that into one giant prompt, and generate one final answer. So yes, there's a lot of like cars related questions. What is this? Oops.
You have to run the previous.
No, actually, I think I broke this one while I was sitting there. But this is what it does in a sense. I can show the source code. So it'll take this list of RAG models, generate a response from them, then throw it into this final prompt.
So both RAG models are of same class, meaning like a text classification,
You can-
searching and stuff like that. In your case,
Right now, yes.
but later on you can do two different things.
They're just different roles they are playing. So, for example, one could be answer the question from the perspective of a professor. Another could be answer the perspective from a perspective of a educator who's trying to explain it to a 10-year-old. Another could be things like that.
The thing is, like, this is very high level. So something you could do is use a very simple model to generate an explanation for what the user wants in the query. Then take one of the bigger, like say, like you can run Mixtral's the 80 billion model on this. So you would run that and have it only generate code, and then have like Claude 3 interpret that code, and that's your response. And then this is a lot of these tools. I feel like I think they do exist. This just puts RAG into it a little easier. But that's it essentially. This is the.
Can you go a little bit to the query part? What are you doing there? The last one in the same part.
Oh, this is just a whole bunch of So the code structure is going to it's not something I can explain.
Oh, okay, sorry.
Yeah, it's there's a whole bunch of internal classes that
I got it. I thought you were generating the code, but it looks like the string ends right there.
No. This is just the prompt itself. This is the whole prompt. So yeah, that's there's this as well. This is kind of stupid, but there's this chat thing which just takes and now you're running this. Okay, so now you have this whole chat pipeline, or this whole RAG pipeline in a chatbot, which is, and you initialize it the same way and import this chat class and just wrap the RAG in it. Yeah, that's everything. Nice.
So, I mean, it's now all the circles not open source now. It's all
It was. I'm going to gatekeep it now for a little bit, so not at the moment.
Till you guys finish your labs. After that, we'll think.
Oh, so he's not going to post this on the Slack channel?
No. You're not likely to do your lab at all. I mean, your project at all. If you see it.
But I saw you posted somewhere.
Yeah, I did. That's
don't-
completely different one that what
Okay,
this
I have
is.
that in my laptop.
That's that's fine. That's fine. That's not this.
That's a teaser. It's a teaser.
How long did it take you?
I started this in like the library itself. It's not just this RAG pipeline. It's a whole bunch of other things. This colored text, and I started the library in November, so it's been a while.
So when you say library, it's like a Python library. So you make it as like a PyP, and then I can.
Yeah. Yeah,
Just
it was until yesterday.
It's nice. It's actually great work.
Yet
Yeah,
will I have to
great.
tell him that nobody will learn if you do that.
Yeah, that's why you asked it.
Exactly.
Thank you.
Yeah.
Right. Good.
Guys, I want to just say one thing. I don't know if you realize this is a complete solution, more than the complete solution to your first project. He has added personalities to it, different persona and so forth. So, and it may, I don't know, it may surprise you to know that this is a freshman student in college. Okay. So, who's very, very busy with a high academic load, okay, and still manages to do all this. So, it should give you some motivation that all the spare time that you waste.
It demotivates us.
You have high school kids in the class, customers, and next time you should let us.
Oh, we have.
Who we are competing with.
Yeah. No, but it's always true, right? The younger people they have less complicated lives.
Yeah.
Right? Like Hama doesn't have kids and family yet, or a job or boss to babysit.
Exactly.
So, well, that's that. So, all right, guys. Any feedback? Anything? How do you guys feel about this?
More than 24 hours in a day, that's what I need.
Getting more intense.
Yeah, so that's a feedback. Actually, I need a bit of a feedback. See, guys, I'm running this boot camp, and at the end of it, before the boot camp starts, everyone, many people will come and say, 3 months, can you not compress it down to 1 month? And I always say no. But are you guys feeling that it's just the right pace, or you feel it's way too fast and we need to go more relaxed?
Good pace.
It's a good pace. Okay.
I have one feedback.
Yeah.
Maybe I don't know. It's a personal one. Probably like I don't know about others related to the project.
Mhm.
Okay, so at least like for the last 2 weeks, I've been spending 70% of my time in sort of like a DevOps work,
Mhm.
not actually like doing things.
course.
Okay,
Yeah.
that is literally like I don't know, like I want to call this like a waste of time, though it is like good to know. But if the servers or the systems, we have sort of like a template or the recipe to get that like the systems of the infrastructure, whatever is necessary.
Yeah.
That help us to do more on the project.
More on the project. Yeah.
Okay.
So,
So
yeah.
this is where like the times mostly we are
Lot of
spending.
time spent.
And the second one is, of course, I don't have a very I'm not current on my programming skills. So that took like another 20% of my time. So now I can sort of like
Get
I was
going.
crawling, now I can walk at least.
That's good.
Right?
That's good.
So these are the two more major component of my time I spent. If you can reduce that infrastructure part, that
Yeah.
would help us to.
That is
move
right.
forward.
That's a good feedback. Ganges here said that it takes quite some time to just get the environment going and other things going and so on and so forth. So first of all, that's a valid thing. I'll do whatever I can to reduce it going forward. Now, having said that, there is one reality in our world, guys. Those of you who remember when big data came out, the last big technology, anybody remembers downloading Hadoop from the Apache website, getting somehow HBase to work and so forth? What did we do most of the time? Were we writing nice, elegant Java code, or what were we doing? Yeah. Most of the time we were struggling with the thing, because what would happen is we would have one version of this library, one version of that library. They wouldn't work together. Then documentation wasn't perfect, etc. See, the problem with the setup environment here is In December, I had set up, after the last bootcamp, I'd set up all of these machines perfectly. It worked with that version of the libraries. Time flows. And the moment you update your Python, now PyTorch itself has to catch up. Every library, so it's very hard actually to keep a pre-cooked environment. But what I can do is create a single recipe book at any given time that just follow this set of instructions and your environment would work. Or the other thing, if I had the luxury of staff here, lab assistants and staff here, they could have pre-set up each of the machines with that. And I'll try to do that next time. But with this, really things are so fast moving that whatever environment you start out in the beginning of the bootcamp will not work 1 month later. So what libraries are moving too fast.
Asif, Asif,
Yeah,
you're
go
still YouTube live casting if you want to pause that.
Oh, yeah.